Hey everybody, in this video, we are going to introduce ourselves to two constants, the acid dissociation constant and the base dissociation constant. And these two constants are very important for Unit 12. So essentially, this video is a preview to Unit 12 in a way. Now, without further ado, let's get started. So, our acid dissociation constant describes an acid forming hydrogen ions. So, this reaction shows the aqueous form of the acid dissociating, or more specifically, ionizing, to form H plus and the respective anion, since if you think about it, the plus and the minus add up to 0, and the left side is neutrally charged. So the charges make sense, and that's one way to keep track of your charges to see if they're balanced or not. So if you release an H plus, then you have a corresponding A minus left over. Now, the Ka, or the acid dissociation constant, is products over reactants. So Ka is equal to the concentration of hydrogen ions times the concentration of the anions over the concentration of the acid dissolved in water. Now, for weak acids, we know that the reaction typically does not go to completion. So at the end, some amount of HA, or a generic acid where H is the hydrogen and A is some type of anion, such as F minus, or maybe the acetate anion. So at the end of a reaction for a weak acid, some amount of HA is in equilibrium with the ion. So this is in equilibrium with this. And because at the end there are two things in equilibrium, we typically write these weak acid dissociation reactions with double arrows. And for this reaction, we could say that the Ka is 0.1, and usually for weak acids, the Ka tends to be less than 10. Now, what about a strong acid? So for a strong acid, we know that this reaction from strong acid to the respective ions goes forward 100% or very close to that number, or forever until all the reactants run out. So there is not really an equilibrium between products and reactants, since reactants essentially don't exist by the end of the reaction since it's 100% through. Because of this, we typically see the dissociation or the ionization of strong acids with forward arrow. Typically, we use forward arrows when a reaction is nearly 100% complete, such as this one. So we use equilibrium arrows when a reaction stops at a point where both products and reactants exist, and they are in equilibrium. So since all of the reactants are essentially gone and there is no such equilibrium between reactants and products, we typically write the ionization or the dissociation of strong acids using a single arrow, since they essentially just go forward until they stop. So there's not really an equilibrium there. And for strong acids, these Kas are typically greater than 10. So, for example, it could be 10 to the 6, which is pretty high. So, what does it mean to have a high equilibrium constant? Well, that would mean that, well, for example, if it had an equilibrium constant Ka of 10, this means that there are 10 times as many products than reactants in general. So that's just like a vague assumption, but generally, an equilibrium constant of 10 means that there are a lot of products compared to reactants, or about 10 times as many. But of course, that's not an exact number, and you have to calculate it on your own. You know, honestly, I don't know why it's called the acid dissociation constant, because these things are actually ionizing or turning into ions from a neutral compound. So I don't know why they say dissociation, but technically this process is ionization. So if I were you, I would call this process ionization, even though they like to use the acid dissociation constant, which has the word dissociation in it. I mean, it is kind of, but more appropriately, it is actually ionizing and not dissociating. So what about our base dissociation constant? Now this describes the formation of hydroxide or OH- from the base. So we could look at a weak base reaction first to see how the Kb works. So for weak bases, we know that not all the weak base reacts with water to form OH minus completely, so it's not a 100% yield process. So for example, we have ammonia in its aqueous form reacting with water to form NH4 plus and OH minus. And this should ring a bell if you watched video 2.6 about electrolytes and non-electrolytes. And if not, maybe this is your first time, well, here is the reaction between weak bases and water to form hydroxide. So this is why NH3 is a weak base. It's because it reacts with water to form hydroxide. And remember, bases form OH minus. So we could write the Kb for this reaction, so it would be NH4 plus times OH minus over NH3. So that's what the Kb of NH3 is. Now, this is the general equation where B could be something like NH3, and this could be something like NH4 plus, and this will always be OH minus. Now, the Kb for this reaction is 1.8 times 10 to the negative 5. So it's not a very thorough reaction. Not all of the NH3 will become the NH4 plus and OH minus. So it's typically less than 10 for a weak base. Now what about strong bases? Well, strong bases have a Kb of greater than 10, and in general, all the metal hydroxides are all strong bases, no matter how soluble they are, because if they dissolve, they will separate into ions, and thus they will be strong electrolytes as mentioned in video 2.6. And because salts dissociate completely, such as sodium hydroxide dissociating completely into Na plus and OH minus, they are considered strong bases because they form ions, or the OH minus, nearly 100% of the time. And because they form ions nearly 100% of the time, you essentially have no sodium hydroxide in its aqueous form. Instead, you have the ions in their aqueous form, and because of that, you essentially have no reactants, and thus there's not really an equilibrium that is ever established. I mean, okay, technically there is for strong acids and strong bases, because there is a tiny amount of strong base or strong acid in its aqueous form at the end, but it's so tiny that essentially for the entire reaction, the reaction just keeps on going forward and forward until it stops. And because of that, we essentially use a single arrow because the reaction is most of the time never at equilibrium, because it just goes on and on until all the NaOH, for example, just disappears. So this is the reaction for the formation of OH minus from sodium hydroxide. Notice how it doesn't have to react with water this time, and bases can do that. As long as a base produces OH minus, it will always be considered a base. So this is the Kb expression for the sodium hydroxide, and remember how I said that the reaction goes nearly 100% of the way? That means that our NaOH will be super duper small, and because of that, our Kb will be super duper large, which is why it's a strong base, which means that it has a Kb typically greater than 10. Now, let's do an example problem involving acids and bases. Well, in this case, we're just dealing with a weak acid. So, the Ka, or the acid dissociation constant of ammonium, NH4+, is 5.8 times 10 to the negative 10. So from that number, we know that it's a weak acid because the Ka is less than 10, so we can use a double arrow to show that it does not ionize completely. Now, how do we write the reaction from NH4 to it releasing H pluses? Well, you could imagine your NH4+ splitting into H+, and what are you left over with? Well, you're left over with an NH3. And notice how the charges on both sides are equal, because this has a +1 charge, and on the right side there is a +1 charge. So the charges are equal, the chemicals are equal, so the reaction is balanced. So we could write a Ka expression for this, and you get that. And it's equal to this number. Now, I want you to find the H plus at equilibrium, so note that at equilibrium, if 50.0 grams of ammonium chloride is dissolved to make 312 milliliters of solution. So I did all the math and I calculated how many moles of NH4Cl that was. So grams times 1 over the molar mass to get the moles of NH4Cl. And because there is 1 mole of NH4 plus and 1 mole of NH4Cl, they are in a 1-to-1 ratio. So that means that if I have 0.935 moles of ammonium chloride, that means I have 0.935 moles of ammonium. So I can find the concentration of ammonium by doing some math. I take the moles of ammonium over the volume of the solution and I divide them. And remember, this is in liters, and I get 3.00 molar for the concentration of NH4+. Now let's calculate the Q to see if the reaction, which is this reaction, will move forwards or backwards, because it's clearly not at equilibrium. So initially when we start off, we of course are dissolving it in water, and water does not have any H pluses or NH3s in it yet, but when we dissolve the NH4Cl, we have some NH4 plus to start with. So we started off with 3 molar of NH4 plus, and we have no H plus and no NH3. Now there is technically some H plus because water can self-ionize, but let's not talk about that for now because we will save that for Unit 12. And anyways, the self-ionization of water will create such a small amount of H plus that we just consider the amount of H plus we start with to be 0. And this will all be discussed in Unit 12 as I mentioned earlier, since this is essentially just a preview to Unit 12. So don't worry about those small details and just plug in the numbers. So we know it's 0 times 0 over 3, that's 0. So obviously since 0 is less than K, or the Ka to be more specific, that means Q is less than K, and because of that, the reaction will move forwards. So now that we know that, we can create an ice chart. So here's the reaction, and it's going forwards, so this will be minus x, and these two will be plus x, and they're all 1 because the coefficients are all 1. And we do the math, so we start off with 3 molar of NH4 plus, and nothing of the other two, and we do math. We say for every 1 molar of NH4 lost, we get 1 molar of NH3 and 1 molar of H. So we get these 3 expressions as the new concentrations at equilibrium. So we simply chug that into the Ka, and we set it equal to the Ka as shown here. So x times x, which is NH3 and H plus, all over NH4 plus, which is just 3.00 minus x. And we set it equal to the Ka, which we know is that, and we do some simplification, and we distribute this here to get this part, and note how I'm still keeping track of sig figs, because 3 times 5.8 times 10 to the negative 10 is 1.74 times 10 to the negative 9, but I have 2 sig figs, so I have to underline it here to make sure that my sig figs are consistent. And I move around my variables so that 0 is on one side, while I have a quadratic expression on the right side, and that means I can use the quadratic formula since there doesn't seem to be another way. So I use it, and I still manage to keep track of sig figs, and I plug in the numbers, and I kind of simplify them, and in the end I get this. And you know that there are 2 solutions. So I get x is equal to 4.2 times 10 to the negative 5, or x equals negative 4.2 times 10 to the negative 5. And since we know that x is the concentration of H plus at equilibrium, and we know that concentrations can't be negative, so this means that x cannot be negative. Instead, x will be 4.2 times 10 to the negative 5. Now at the beginning, we said that the equilibrium concentration of H plus is equal to x. So this must mean that the concentration of H plus at equilibrium is equal to x, or 4.2 times 10 to the negative 5. Now that's all for this video. We will talk more about acids and bases in Unit 12, so don't worry if you did not get all of this. So that's all for this video. Have a nice day, everybody.